Welcome to Study Loop.
So in this question, air flowing at a specified supersonic Mach number is forced to undergo a compression turn or oblique shock. The Mach number, the pressure, and the temperature downstream of the oblique shock are to be determined here. So as the above assumptions, we have three assumptions that we have to see. First one is that the flow is steady. Second one, that the boundary layer is thin. And the third one is that the air is an ideal gas with constant specific heats. So similar to the previous questions that we have done, the specific heat ratio of air is K is equal to 1.4. Now because the boundary layer of the wedge is very thin, the deflection angle can be considered equal to the wedge half angle, and that is equals to theta is equals to 15 degree. So the possible values of oblique shock angles, that is beta, can be found out using the formula tan theta equals to 2 of ma1 square sine square beta minus 1 upon tan beta divided by ma1 square up into k plus cos 2 beta plus 2. So keeping these things, we have for beta weak, we get it to be 45.34 degree, and beta strong, we get it to be 79.83 degree. Considering these two angles that we have, we can now find for weak shock. That is, for weak shock, we understand that ma1n equals to ma1 sine beta, that is for weak beta, and that is equals to 1.423, and for strong shock we have ma1n equals to ma1 sine beta, and the value is 1.969. Okay, now for downstream, normal Mach number, that also we have to case the case of ma2n, right? So again we have for weak shock ma2n equals to k minus 1 ma1 square n plus 2 upon 2k ma1 square n minus k plus 1, and the value that we get is 0.7304. Similar for that, we have for strong shock, and the value is 0.5828. The downstream pressure and temperature that we have to find out for weak shock. P2 is equals to P1 2k ma1 square n minus k plus 1 upon k plus 1, and that is equals to 17.6 units. Then as we move for, then we have for the temperature that we have T2 equals to T1 P2 upon P1 rho 1 upon rho 2, and the answer would be, for this case it would be 610n. This is for in the case of weak shock. When we take the case of strong shock, we get P2 is equals to P1 2k ma1 square n minus k plus 1 upon k plus 1, and the value is here 34.9 units. Then for temperature it is P2 equals to T1 P2 upon P1 rho 1 upon rho 2, and the value here is 798 R. So the downstream match numbers also we have to find out, and that is also the weak shock and the strong shock. For weak shock, we have Ma2 equals to Ma2n upon sine beta minus theta is 1.45, and the second is for strong shock, and that is Ma2 equals to Ma2n sine beta minus theta. So this will be a basis of only strong shock, that is 0.644. So these are the values that we have to find out. I hope you understood. Thank you.